back and then memorize the textbook one more time. Okay, yeah. So this is the setup time, hold time, and clock to queue. Okay. Now, then let's just quickly review one more time what we did last time so that we can continue, right? So we say that we have this combinational logic and we have the register, and our goal is that we need to have the time, the period larger than the clock to queue, and also the setup time, and also the delay of the logic, right? So because from here, you first need so much time to propagate, and you need to stable for T setup, right? Now you understand why. For example, for this circuit, the reason that you need to for so long stable for T setup is just because I need to propagate into here so I can copy, right? So after setup for so much time, then you copy. After copy, you still need to go through some register, some transistor, and then it is ready. So to go through a loop, you do need to have the period larger than that. And more importantly, you also need some hold time, because in this case, in this particular case, sometimes your delay through the combinational logic is very short. Now, if they are so fast, then it can be that once I copy, then you go so fast, then you change the input. And when you change the input, you screw up the setup time, right? You change the input and we still have not fulfilled the setup time. This is just like a racing condition. If you have a feedback, right? And then now you go in so fast, maybe it will just erase this one. When I was trying to copy to here, right, during the setup time, you already changed the D, right? So this is when you have a feedback. That's an overall overview, right? So I hope you understand. If you have questions, let me know. Okay. Now let's start doing one by one, right? So how do we reduce the load? We only look at the master slave flip-flop, right? So this is the transparent low, this is transparent high, right? So you can see that we need to drive many switches, right? We have the 8 to drive. So then we come up with this. Can we reduce this load by this? This is also valid, right? So first of all, when the clock is low, right? When the clock is low, then what happened? This is then clock bar equal to 1. So this is on, this is off, and here this is off, right? This is on, right? Because the clock is low. So in this case, the data will go through here, but brought by here, right? And then when the clock becomes high, so clock bar becomes low, what will happen? This one will be closed, this will be on, this will be closed, this will be on, and then you copy this one to here. Of course, we don't just copy, right? You see that we do have a feedback to store, right? Do you remember what do we call this? Is this a static memory or a dynamic memory?
Static memory.
Static, yeah, thank you, right? So it's a bistable, it store the data itself, right? So again, based on this, you see that this is a positive edge trigger. Okay. But what is the problem of this one? Right.
Wait, how do you see that it's positive edge trigger from this diagram?
Because when the clock go from 0 to 1, the data appear at Q.
Oh,
right?
Okay.
During 0, you just hear, so you don't see it, right? Because you're seeing from outside. You don't know what happened inside. And then once it becomes 1, then you copy to here. And what he change here, this is block, you cannot go through. So see, I actually have some wrong label, but you guys did not remind me. This is wrong, right? When the bottom is on, the top is also on. I'm sorry for that. When this is off, both off, right? When it is on, both on, because this is clock bar. This is on, this is off, right? So you see that how you change. So what are the problem? The problem is this. It can have a backward conduction when the T2 turn on. Or just called back conduction. Because there's no buffer. Think about this. When T2 is turned on, you might have, let's say, try to write 1 here, but it might be originally it stores 0. Right? You try to write 1 into 0. But when you turn on T2, then 1 is 1, another is 0. Right? So what will happen? Then what should be the answer? So that's why you see we make I1 much larger than I4. Right? Why is that? Because I1 is stronger, so you will pull everyone to 0. But if you have a wheel, you can see the transistor. You probably see that when this is 1, for I1, I have a big PMOS, which is trying to deliver 1 to the node. And then for I4, I have a smaller NMOS. Right? This is I4, this is I1. They try to compete with each other. But if I1 is larger than I4, this node will be closer to VDD. And then you will overwrite. And that is why, if you remember what we say, that is like overpower by overpower. Right? In the original circuit, do you remember what we call it? How do we write the data into the, what just now, what you said, the bistable, the static latch, the static memory? How do we write it? We cut it off, right? And then we write it. Here, we write it by overpowering, right? By overpowering, we reduce the transmission gate by half. But however, we need to be careful about this design. Okay, any questions? Okay, I assume it is clear. Try to follow everything I said. Make sure that you understand, okay? Okay, now let's have another thing, right? This one actually is very similar to this one, except that not similar. This one is similar to this one, except that we only use the pass gate instead of the transmission gate. Okay. And now can you tell me whether it's positive or negative edge trigger?
Negative edge.
Okay, can you explain to us why it is
Because here when the clock is 1, then this clock bar should be 1, so the clock should be 0 to get the data till Q.
So when the clock is 1, this is on, right?
Right.
Good. And then this is off, right? Very good. Yeah. So when clock is 1, the data will pass through. This is right by cutting off, right? Cut off instead of overpowering, right? At this time, this one is off and this is on. So this one keeps storing the data here, right? And then when the clock becomes 0, clock bar becomes 1, then this is off, this is on. So this one will store the data that it has written. But now this is on, so this will go through to Q. Okay, and this is off, right? So it means that when it is high, D copy to here. When it is low, here copy to Q. So you overall your feeling is that it suddenly copy the data from D to Q when the clock goes from high to low. Okay, so that is a negative edge trigger register. Okay. Now then what is the problem? Right? So what is the problem of this circuit that we try to it's not the problem because it's negative edge trigger, right? It's just opposite to what we studied. The problem is now we actually have changed the circuit a little bit, and the problem is when you have overlapping clock. So what is overlapping clock? I think I mentioned last time, I kind of forgot. Yeah, but let me mention one more time, right? So this is the clock, and then it goes through an inverter to generate another clock. The ideal clock will be something like this. When you are low, I want to be high. When you are high, I want to be low, right? And then when you go down, I go up, right? So this is ideal. But unfortunately, there's always delay. So then we have a region where both of the clock are on. This is called 1-1 overlap. We also have a region that both of them are low, which is this region, which is 0-0 overlap. And you can have problem in different clock, right? So what is the problem when you have a 1-1 overlap? When you have 1-1 overlap, it means all of them are on, right? So you have 1-1 overlap, both clock and clock bar are on, all transistor on. Then you have the conduction from D to Q directly. That is a problem. Then it is no longer an edge trigger register. Think about if this is long enough, overlap is long enough, it can propagate all the way, then it becomes a latch. And that will be a problem in our circuit. Okay. And of course, another thing is the conflict once they are on at the same time. Right, this is 1, right? You are going to have a conflict between, for example, A and D. Why? Because this both are turned on, right? Let's look at this. You want to write 1, for example, but originally you store maybe, right? This is D, this is A. Let me still draw the transistor. This is B, and now this is on due to overlap, right? And originally this is 0. I want to write it, and this is 1, this is 0. If there's no overlap, I'm going to cut off this transistor. Then you just write it. But now this is driving 0. So again, we have the similar situation like here. Even though we add more transistor to avoid this problem, but because of the clock overlap, I will run into this issue. Is that clear? Any questions? Okay, right. So what we can do, we can try to generate long overlapping clock. What is the meaning of long overlapping clock? This time the clock is not just clock bar is not just generated by inverter. I just use some sophisticated circuit technique, maybe use NOR gate, all these things to generate a clock that I'm sure that they won't overlap, right? So you see, they never have 1-1 overlap, but it does have 0-0 overlap. But for this circuit, it's okay, right? Not really okay. I will tell you why it's not okay, not 100% okay. But with no 1-1 overlap, then I don't have the competing issue, both turn on, and the D also won't go to the Q directly. But what is the problem of 0-0 overlap, right? A lot of what is the problem? That is because now this node will be cut off. Here will be cut off. Let me call this X, right? For example, node X, right, with 0-0 overlap. For example, node X will be cut off. Maybe I should not say this. What I more mean is this X, okay? This one is not really what I want to say. Is floating, right? Like once this is off, let me call it node Y, because when you study, you don't know what cross I'm talking about, right? Node Y. At this point, I'm supposed to store something, but it is floating. And this information can be gone. Now, combined with what we learned earlier, can you tell me why this node has problem if it is floating? Let's say the overlap is very long, then we are going to lose the information. We already learned a lot of device physics, right? Why it will change. Let's say it was at VDD. Do you remember? I hope that you will, maybe you're just too busy or you don't want to answer, right? To try to answer, which is fine. Especially some of you already have been keep answering me question. I appreciate that. But I do want you really to see this now, right? After this class, I want you to be different from people who did not take this class. Even put a cross here, you realize that this is a transistor. And this transistor has the drain connected to here. So you do know that, hey, I have this transistor, which is NMOS. N plus. Yeah, this is PHI1 equals to 0. The transistor is off. No problem with that, right? But I do remember that my well is biased to 0 volt, okay? And this is my Y, maybe at VDD. What is the problem? The Y is floating, so there will be a leakage current, right? So there's a reverse junction leakage. So that is one example. Of course, we also talk about the capacitive coupling effect. All the concept you learn in the dynamic logic applies to here. Okay, any questions? Okay, so if no problem, let's move forward now. Then, so Yeah, so there's always pros and cons. You cannot solve everything, right? And now let's go to another set of a device. I want you to learn because this is very commonly used. SR flip-flop, right? It is a set reset flip-flop. Let's look at what it does first. When it is let's look at 1 and 0, right? Set and reset is kind of contradicting to each other, right? I want to set it and also reset it. So if I say I want to set it and then I don't want to reset it, then it's very simple. I make Q equal to 1. I set it, and then Q bar equal to 0, right? So it can be constructed using a coupled LAND gate, right? And then if I say I want to set it with 0, and then I don't want to set it and want to reset it, then I set it to, then I make the Q equal 0 and Q bar equal 1, right? What if both are 0? As a LAND gate, if both are 0, you're not going to change anything. So that is also logically making sense, right? I don't want to say I don't want to reset it. Then it means just keep it. Whatever you have before, you keep it. But they do have a forbidden state, which is when you say, I want to set it and reset it at the same time. Now you see that this one doesn't have really a big problem because it does. If I put 1, 1, it's a NOR gate, right? It's a NOR gate, right? So if this is 1, output is going to be 0. And if this is 1, this is 0, output is 0. So you do have 0, 0. The problem is, what if you enter into this 1, 1 state and then you change to 0, 0? You will have a problem, okay? So for example, this is 1, this was 1, as I said, this was 1. So this is 0, this is 0, 1, or 0 becomes 1. So this becomes 0 after negation, and this is 0, right? This was the original state, right? We say this is forbidden, we should not have this. But the real reason that you should not have this is when you go from 1, 1 to 0, 0. Right? 0, 0 is valid. You just say that I don't want to do anything to my system. I want to keep it. But what will happen? If this becomes 0, 0 and 0 becomes what? It's NOR gate, right? Then this one becomes 1. If this one becomes 1, then this becomes 1. And if this is 1 and this is 0, this is 0, right? And then this go back to 0. So looks okay, right? But the problem is, in this case, I assume the top one is faster. But what if the bottom one is faster? When, right, you go to 0. When this becomes 0, then this one will become 1, right? Because I have 0 here, and originally it was 0, so this is 1. And so it means this one become 1. And then if this is 1, this is going to be 0, right? And then this one becomes 0, which will still give me 1, right? So the green one is the bottom faster, right? And then the red one is the top faster. So you don't know which one is faster actually, right? It all depends on the process, right? And in principle, ideally, if they are at the same speed, then you will have a big problem. They went to an undefined state. So that's why in set reset flip-flop, right, we can never go to 1, 1, cannot never put in 1, 1. Otherwise, there will be a problem. Okay, any questions? Now, then we also have a clock version of set reset flip-flop. Okay, this one is like this, right? Very complicated, right? But looks like it's not really that complicated because this is a transistor. Here we have not implemented the transistor yet. This one is already 8 transistor, right? For LAND gate, 2 LAND gate, right? So here we also have 8 transistor. So it is similar actually. But then we actually have 2 clock to control it, right? Here is not controlled by the clock. What does it mean? It means that when clock equals to 0, when clock equals to 0, you only have this circuit left. And you see that this one we were going to learn earlier, this is like the SRAM. So you actually have a couple pair. One is the inverter on the left, and then its input goes to the inverter on the right. Okay, and this gives you not Q and Q. This is not Q and Q. So when clock is 0, nothing happens. When clock equals 0, it just keeps the state. Okay, and only when clock equals to 1, when clock equals to 1, then the whole thing becomes something like this. This time I'm not going to draw the couple inverter in details. I just draw this symbol. Right, this is Q, this is not Q. Because the clock is on, so this one brings me to the set M5, right? And this one brings me to the reset M7. Do you see that? Is that okay? Right, because the M8 and M6 are on, so they are just wired, right? So I go to here. And then depends on set and reset, I can change the content. So this one again is through overpower. And you can only do that when clock equals to 1. That's why it's called synchronous, right? By overpowering, for example, I make the set high, then I will draw this to 0, then Q bar becomes 0. And when Q bar becomes 0, Q will becomes 1, right? And I only turn on one of them at a time. I cannot have set and resets turning on at the same time. And that is the same issue like here. I cannot have set and reset turn on at the same time because logically it doesn't make sense. And also from circuit point of view, it doesn't work. Okay, but how do we overpower it, right? Let's look at an example. For example, I try to set it. Set equal to 1, reset equal to 0, right? So I have this set here, M5, which is VDD, which is set. And then the problem is this one, M1 and M2, right? They try to keep the original value. Maybe it was at 1, so M2 will try to compete with me, right? Remember here, I do have M1. This is M2. This is M1, but M1 is at off state, right? Because the input is 0. So for this point, right? What do you want to do if I want to set it? I want to set it so that Vx is larger, actually smaller than the Vm of M3 and M4. That is because this Vx is connected to M3 and M4. Right, because this is, or Vx, I mean, maybe let me just call it Q bar, then you won't get confused, the Q bar. Right, because this point is just this Q bar. So when I try to change this content, I need to pull down the potential. How do I pull it down? Just a potential divider. So I need to make this strong enough so that I can make Q bar, which was 1, to be less to the Vm of M3 and M4, because this Q bar is fit into M3 and M4. Once it's less than the Vm of M3 and M4, then I will be able to switch the output, right? Remember the Vm is when input equal to output, right? So when it's less than Vm, then I will switch the output to another state. Then another feedback will bring the circuit to the state that I want. So that is how we override by overpower. right? So you can see that for this one, sizing is important. And now you see that how we were able to save 2 transistors, right? Because the clock, we don't care about clock, right? We say synchronized. So we have 2 less than this NAND gate, NOR gate, right? That is because we need to just do the sizing properly. Okay, any questions? Is this clear? Okay, if that's okay, then let's move forward, right? Now, so we will continue to